All right, welcome. In this video, we're going to go ahead and derive the equations of constant acceleration and then put them to good use for some rocket science, which is really the point of it all. So to begin, we're going to consider a graph of an object's velocity against time. So we'll plot velocity on this axis. And let's just say we're going to measure it in meters per second, although it could be any units of velocity, miles per hour or whatever, against time on this axis. And so time is going to be measured in seconds. And we're going to consider the motion of an object who starts at a non-zero velocity. So let's say like this is 0 seconds of time, 0 meters per second of velocity. So something is starting out like this and increasing its velocity uniformly. So it's just going to pick up speed like that. And so it starts with an initial velocity, we'll call it v sub I. It's going to end at a velocity up here. The final velocity over this way, v sub f. Remember that on this axis, we're plotting velocity in meters per second. All right, so it increases its speed from this velocity to this velocity over this time here that we'll call t. All right, so that's sort of the setup here. So from this, we're going to derive the equations that are sort of spelled out on the other chalkboard over here. We'll sort of relist them like this. So we need two important ideas when it comes to graphical analysis. And the first is that the area underneath this curve will give us the distance that's covered. So like if you increase your speed, and let's think about this like we're going 35 miles per hour on a residential road, and we're going to speed up to 55 miles per hour as our final speed because we're verging onto sort of a highway. Well, it takes some time to do that. We're also going to cover some distance in doing that. And an engineer might need to sort of determine how long do I build this ramp, because cars will be, covering about this much distance if they're going this fast. So there's sort of real world applications as well. So the area underneath this is the distance traveled. You kind of think about it like when you do an area, you do length times width. So if we just sort of had something traveling at just some constant speed, okay, for a time, then it would just be that velocity, the length times the width, the time, that would give us the distance traveled. That's no acceleration there. That's just if something travels at this speed. So if you just post at 70 miles per hour for a couple of hours, you'll be 140 miles away, right? You go 70 miles per hour for 2 hours. That's 70 miles per hour times 2 hours. That's length times width. So the area gives the distance, right? Kind of think about that. The same is true if we're increasing our speed. We just have a sort of a different shape. We don't have just a length times width rectangle. We also have this sort of triangle on top. But the strategy to calculate the distance traveled is still going to be the same. You take the area underneath that curve, the sort of rectangular area, that's the distance traveled from the fact that it was just going at this speed initially, plus this extra sort of triangular area, that's going to be the extra distance that's covered by virtue of the fact that we're actually picking up speed the whole while, right? We're not just staying at this constant speed. So that's the first idea. The area underneath gives distance. Okay, we're going to use that idea to derive two of the equations. The other idea is that the slope of this is going to solve for the acceleration. You could imagine that I could increase my speed much more quickly. So I could increase my speed from 35 to 55 over much less time if I could accelerate sort of that much more. And the steepness of this line indicates that acceleration. In other words, I'm accelerating more quickly. I'm increasing my velocity over less time. So that's a higher acceleration. So the steepness or the gradient, the slope of this line gives acceleration. So that's really sort of where we can begin. We can say that acceleration is the rise over the run, okay, the slope of this line. So the rise is the difference in the y value. So from VF to VI, or increasing from VI to VF. So the difference between those would be VF minus VI. And we do that the run, right? So that's the rise over the run from 0 to t. So t minus 0 is just t. So this is just the definition of acceleration. It's the change in velocity per time. And we rewrite it with no fractions and with no negative signs. So if you were to just sort of do a little bit of algebra, multiply both sides by t, add vi to both sides, you would get that the final velocity of an object that's accelerating uniformly is equal to its initial velocity plus acceleration times time. So acceleration times time is the extra sort of bit of velocity that we're adding to our initial velocity to give us the final speed. So it's like if you're going 35 miles per hour, your car can accelerate at 2 miles per hour per second or something like that. So this usually always meters per second, the SI unit. But in America, if you're a car commercial, this car can accelerate from 0 to 60 in 10 seconds. So that's telling you the acceleration, so it can change its speed from 0 to 60 in a certain amount of time. It's reporting its acceleration sort of on units, miles per hour per second. So we'll just keep meters per second or meters per second squared. Remember, the important thing for us with our rocketry is that the accelerations that we're going to be relying on is going to be a known value. So this is going to be a known for us. What's the acceleration here on Earth? Let's hear it from the e-learners. Unmute your mic. The booming voice from above resoundingly tells us. Correct. Was 9.8 meters per second squared. You got it. That will sound fine on YouTube. That's what I have. 9.8 meters per second squared. So just kind of think about this. This would be like, something increasing its speed, but it's like, well, gravity could do this too. If you just sort of look at an object that's sort of already moving and then it picks up speed under the influence of gravity, gravity's going to accelerate this planet. It lets it fall, gravity's going to pick up speed. So that's important for us to sort of keep in mind. This is our first equation. The data that we're collecting out there, remember, is the time airborne. And so by measuring this and by knowing that the acceleration due to gravity on Earth is 9.8 meters per second squared, we can calculate the initial velocity of our rocket by understanding that gravity is going to eventually slow it down to a stop, right? And so we launch a tennis ball up into the air, it reaches some maximum height, and then it falls back down, okay? We know that gravity is the accelerator that one, slowed the initial velocity down to a stop right at this point, and then also sped it back up again in the opposite direction. So by us measuring, remember, capital T, the total time airborne, that's really giving us a way to deduce the time to max height, at that point, okay? That's the point that we need to consider because we want to know this conclusion, right, the height of our rocket, and we also want to know the initial velocity vectors, how fast can we sort of launch it this way. So you say, well, here's an equation that tells me everything I need besides my answer. I know that right at this point here, I know that for just a moment, gravity has temporarily stopped this object, right? Like before things can move in the opposite direction, they have to come to rest, right? They have to reach a temporary speed of 0. So we know that here. We know that the acceleration is 9.8, and we want to know this initial velocity, right? This initial velocity. By measuring the time airborne, we half that time to get the time to max height. So up here is where we realize that 2 lowercase t equals capital T. All right, so this is the time to max height t. Half of this time. So it's the one way to think about it. We double the time here to get this time. So if it takes 1 second to go up, double that to get the 2 seconds airborne. This is what we're measuring. So it's really like t over 2 equals t, or 1/2 t equals t. However you want to think about it, right? These are the same equations. And then we just plug it all in here. So it would be VF equals VI plus AT. An important consideration is that this initial velocity upwards, let's call it positive. Let's make our answer positive. So there's a vector nature to this, which means the direction matters of velocity. Up as opposed to the acceleration. So the acceleration is negative if we're solving for this positive. It's arbitrary which direction we call positive or negative. We could have made down positive, and then our answer would be negative. So, oh, we're launching with negative velocity, down is positive, right? Because gravity is the thing that opposes it. That's what's important, that the vectors that oppose each other, one is negative relative to the other. That's a sign convention that we adopted for this. So the final velocity is 0. The initial velocity we want to know, gravity is negative 9.8, and this t, we're going to know its value, right? Because that's the thing that we're going to measure. We're measuring the total time. Now you see we've got a perfectly solvable equation. If you subtract vi from both sides, or can divide, rather if you multiply the 9.8 by t, that's really your answer, right? Because that will be the term that's negative of your initial velocity. So solving this thing for vi is just like adding this to both sides, right? So vi will equal to positive. So we'll just say, okay, let's add that to both sides. Vi equals 9.8 t, where remember, t, lowercase t, is half your time interval. So there's your first conclusion, okay? And it's from just the definition of acceleration, changing velocity per time, all right? That's like equation 1. The next idea is the distance. You know, how much distance is going to be sort of covered here. Remember, we began by saying that's the area underneath this curve here. So get that one out of here. So how can we calculate the area underneath this? We already said that we could break it down to a rectangle and a triangle, and it's the area of these shapes sort of together that solves for the displacement or the distance. So the distance d is equal to the area of this rectangle, which is length, times width. So vi times t. But then we have this sort of triangular part. The base of this triangle is the same as the rise when we did slope, right? It's vf minus vi. So this part right here is vf minus vi. And if you look up here, vf minus vi is equal to at, right? If you multiply both sides of this by t, you find that this is really equal to at. Right? That's just like one step away here. Multiply both sides by t, you get this. So this base here has a value of at. All right, so the base of this triangle, right? We're looking at this triangle right here now. And I know that the area of a triangle for my geometry class is 1/2 base times height. So I have the area of this as 1/2 the base, at, times the height, which is t, right? From 0 to t. So 1/2 at times t is 1/2 at squared. Make that clear. So the total distance, when something accelerates, is equal to the distance it would travel by virtue of the fact it was already going at a non-zero speed. So that's just the non-accelerated part. Distance, velocity times time, distance equals rate times time. But then you got to add in the accelerated part of the motion. So there's extra distance that's covered because we are increasing our velocity. So we have to account for that. And so the final equation then is the distance, d, is equal to this term, vit, plus this term, 1/2 at squared. And you'll see that if you multiply velocity times time, you get meters, right? So velocity in meters per second times time in seconds, the seconds cancels, and we're in meters of distance. The same thing happens here. Time squared is seconds squared, but acceleration is measured in meters per second squared. So in this case, the seconds squared cancels, and we're in meters of distance. So this term gives you the meters of distance you've covered because you're accelerating. This term gives you the meters of distance you've covered because you're already going at a non-zero speed. If you start at a speed of 0, the math just gets simpler. You know, it's like this term just goes away, and you just have like that's how much distance you've covered. So I'm showing you beginning with a non-zero velocity to account for situations where you aren't going to have the initial velocity is 0, just makes it a little bit easier. All right. So that's like equation 2. You can see that it agrees with the one on the other chalk. Now we're going to sort of do something to be a bit clever to give us another equation. So if you look through the equations, you'll find that you relate 4 variables, but there's 5 total variables that we're going to sort of consider here. So each equation leaves one out. Like this one doesn't have distance in it, right? This one lacks final velocity. All right, so each equation is going to sort of be missing one of the 5 variables. So you kind of need to know all of them to solve for the thing you're interested in. So what we can do now is just sort of imagine that if we increase our speed from VI to VF, one way to think about our motion is that we're just sort of going at an average speed of this the whole time. Like, yeah, we were going slower, we ended up faster, but on average, we were just going like this fast. We were just going VI plus VF over 2, like the average of those speeds. Add them and divide by 2. So like this line right here has a value of VI plus VF over 2. It's the average velocity. And so what's the area underneath this? In other words, what's the area of the box that I will outline in tasteful pink chalk here? What's this area? All right, that's everyone's favorite sound. So how do we calculate the area of a box, a rectangle here? What's the length, which remember is this value, times the width, which is still t. So that's not too bad. Remember, we're solving for distance when we take an area, because it's meters per second times seconds. The seconds cancels, we're in meters. So now we've got a pink equation for distance. All right. VI plus VF over 2, which I'm going to rewrite slightly. 1/2 VI plus VF. Everybody okay with that? I'll just sort of factor off the 1/2. Instead of writing it over 2, that's the same thing. Like this, the same thing as that. So length times width from 0 to t. So there you go. And you'll see that that's like the third equation over there, right? So we've got 2 equations that solve for distance, but this one doesn't have acceleration in it, right? There's no acceleration in this equation because we kind of said, yeah, we're not really accelerating. We're just going to average constant speed. So just like this was a constant speed initially that gave us this term, we're just sort of saying, let's average it all out. So see what we did? The area of this pink box includes this triangle here, which wasn't really part of our motion, right? Like we started at this speed, but it leaves out this part over here. The way I drew it, it looks like this is bigger than this, but it's not the scale. Like they cancel each other out. So that's why this works, okay? It's the area under this square is equal to the area of this trapezoid, right? Because we're solving for the same distance. In other words, the distance that you travel doesn't change because we solve it a different way. It's a different way to approach it. Here, we might know the value of our acceleration. Hey, it might be gravity doing it. We know it's here on Earth, it's 9.8, but maybe it's not. Maybe we're accelerating like in a car, like we were mentioning on an on-ramp. Like there's other places where this becomes practically useful where acceleration is important. All right, so to get the last equation, we do a little bit of algebra here. So we're going to go back to this equation, and we're going to solve it for t. Okay, so what's t equal to if a equals VF minus VI over 2? Here's where you do the old algebra switcheroo. You just switch the a and the t. You're allowed to do that. And you say, well, how am I allowed to do that? Multiply those sides by t, divide those sides by a, see how they just kind of switch spots. Okay, so like anytime you see variables like this in an equation, these guys can change spots. That's a legal move. So I have this equation for distance, right? We'll start with that. I'm going to write it right here. I'm just going to rewrite this right here. D equals, but I'm going to go back to this way again. Okay, so like, remember, this term is the same thing, just to sort of reemphasize that. That's the same thing as this. VI plus VF over 2 times t. But t is the thing I want to substitute for. In other words, I want an equation that doesn't include time. See how time's in all these equations? Now I want to have an equation with no time, where things I can solve just like how fast they're going initially, final, in terms of their acceleration and their distance. Like when something covers a certain distance because it's accelerating, it has initial and final velocities, and they're all related mathematically, regardless of like the time it takes to move. And that's what this equation is going to give us. So, did anybody already get it up here? What is t equal to? T must be equal to VF minus VI over A, right? You do the algebra switcheroo theorem. the Schleich algebra switcheroo theorem. I'm pointing that today, here and now. You're welcome, everybody. So plug that in for T here. That's what T is equal to. VF, is that going to bother everybody? I'm doing this in like 2 different colors. Can we handle that? VF minus VI over A. All right, so you got two fractions that you got to multiply. Go ahead, YouTube. We'll give you a head start. Pause the video now. All right, we're back. So the numerator, it's like two binomials we got to multiply, but the denominator is like multiply fractions. Numerator times numerator gives us a numerator. Denominator times denominator gives us the new denominator. I'll take care of the, doesn't matter. I'll have to do the denominator. You guys do the numerator. That's good. So 2 times A is 2A. All right. And then you guys could take care of that numerator. All right, no worries. Go. Whoa, that looks like you could foil that. You guys know how to foil? Foiling is a certain way to distribute, right? So first, outside, inside, last, or that. So that's what we're doing here. VI times VF is going to be VI VF. VI times negative VI is going to be negative VI squared. So we have VI VF minus VI squared. So that's the first and the outside. Now the inside, VF squared plus VF squared. And then the last, VF minus VI. So minus VI VF. VI VF minus VI VF. That's kind of nice. Those go away. Remember, we don't like the negative signs. We don't like the fractions. Remember that all of this solved for distance. So we rewrite this now. Adding this to both sides, multiplying both sides by this. So we have the final velocity squared, like we're trying to get this all by itself. All right, so if we got this all by itself, so we go multiply both sides by 2AB, and by 2A to get 2AB on this side. We also have to add this negative VI squared, right? So you add VI squared, and it's positive on this side of the equation, right? Adding up to both sides. And then we still have this 2AB plus 2AB. And that right there is the fourth equation you see up on the chalkboard over there. So we've got equation 1, which is this. Equation 2, this one here. Equation 3, and equation 4. All right. To answer the essential question, how are we going to use these to sort of answer our rocket problems? We really talked about the initial velocity already. You're just going to take half of the time airborne, lowercase t, times 9.8. That will be the initial velocity. It's going to be in meters per second. To convert it into miles per hour, you times it by 2.23. To solve for the height, that's the distance, right? So the height here is really the distance that it sort of travels. So we can use an equation of motion to solve for this. And the way that we sort of think about it is using this equation of motion. We consider an object that were to just be sort of dropped from that height. So if we launch something up in the air, it reaches a maximum height, and then at that point, its initial velocity is like 0, right? It reaches the speed of 0. So it's just like if we drop something from that height and it fell. By timing how long it takes to fall, we can solve for how high up it must have been, because we know how strong Earth accelerates things. Like, right? Please report to me by it. All right, so we want to solve for this displacement vector. See, this gravity, that's just an example of it. Accelerating still at 9.8 meters per second, every second, 200. All right, so this height here is really like this height. If we're dropping something, its initial velocity is 0. So remember what I said, like Okay, that's nice because then that term just goes away. If 0 is the initial velocity, it doesn't matter how long it's falling, that term doesn't affect the distance. So it just becomes the distance, which we're calling h for height, right? Height is a distance, is equal to, this is 0, right? Because we're considering the tennis ball just as it falls from the top of its flight. That's where it's at maximum height, the distance we want to know, must be equal to this, 1/2 at squared. And you say, bingo. We know that acceleration is 9.8, and we've already got t. We've got lowercase t. We passed our total time airborne. So that's our path to solve this. It's just 1/2 the acceleration due to gravity, right? So sometimes we'll just call this lowercase g. If you look at your notes, you're like, I have it h equals 1/2 gt squared, right? That g is this, the acceleration due to gravity, local g here on Earth, right? So that's your path to solve for the height. Using the time down. Remember, yesterday we talked about using some altimetry, using some trigonometry to also get that conclusion. We'll save that for next time.